All right. Should hopefully be an abbreviated lecture. Let me start by trying to wrap up some of the big ideas that we've talked about either in other videos or in class. In class, we spend a lot of time on Faraday's law with magnetic induction. We've seen things like Gauss's law. We've studied magnetic fields, and that magnetic fields are very similar to electric charges, but have some unique features, like that you can never have a magnetic monopole. You always have a north and a south, where with charges you can have just plus or just negative charges. And then there was also this fourth thing that was worthwhile to talk about called Ampere's law, that unfortunately the mathematics behind it I feel are just a little too much for the intro sequence, so we kind of skimmed past it, but I talked a little bit briefly about it in class. Let me nonetheless summarize all of these four things, because together they actually say something incredibly profound. So we've seen a series of combinations we've seen a series of results regarding the electric field and the magnetic field at this point. For one, we've talked about charges, where you can have positive charges, and then you might have negative charges. And we've said something about, maybe this is Q1 and Q2, and we have talked about how with Gauss's law, if I enclose some charge within some sort of surface, some sort of volume here, so some sort of 3D volume that has some sort of finite area that encloses the entire thing, there are electric field lines that start at the positive charge and go to the negative charge. Some of them might look like that, some of them might look like this. Some might actually go out of the surface and then come back into the surface, like that. Some of them might go out in this direction. I'm essentially drawing a electric dipole in this case. But we saw that the charges can act as sources and sinks for the electric field lines. And if you were to, in a sense, count the electric field lines that are piercing through the surface, that we can now more formally say that as we're talking about counting the electric flux that goes in and out of the surface we've drawn, there was a relationship called Gauss's law that said, I look at the electric flux through this surface that I've drawn in red. That then is equal to the charge enclosed divided by epsilon naught. There is a relationship between the flux, the electric flux going through any arbitrary surface, and how much charge is within that surface. And we saw that by thinking about field lines leaving and re-entering the surface. We could say something about magnetic flux through an arbitrary surface. But we have to remember that the thing we notice as different from with magnetic fields is that you can never have magnetic monopoles. If I have a north pole, there is a south pole attached to it. And if I cut it in half, then there's still a north pole and a south pole in that smaller piece. And if I cut it in half, and no matter how small I get, with every north pole, there is a south pole attached to it. So a way of thinking about that is that no matter what surface I draw around, some sort of magnetic element, which I'm going to just represent as a little bar magnet, for every north pole, there's always going to be a corresponding south pole. And as a result, we saw that magnetic field lines always come in loops. So there could be, say, field lines that can come up out of the surface, maybe go into the surface. But no matter what happens, the amount of magnetic field lines that go out always are matched by the magnetic field lines that come in. We could write that in a Gauss's law sort of argument as saying that the total magnetic flux through the surface is related to the amount of magnetic charge in quotes that's enclosed. But Since every north inside also has a south inside, that must equal 0. This is really just a statement that there are no magnetic monopoles. No matter what surface I draw around a magnetic element, the magnetic fields will always create loops, so that whatever goes out also goes back in. So this flux really seems to be a crucial element. We've talked about the electric field and the magnetic field as these invisible structures that pervade the cosmos, and charges and magnets can cause fluctuations and changes in the magnetic field and the electric field. And really it's accounting for the flux that seems to attach to things like the amount of charge actually that's within the surface, or the amount of magnetic monopoles that's within that surface, which in the latter case is 0. Now, like good physicists tend to do, we also then want to ask about how about the changes in these things. So you could ask about things like changes in flux. Well, we've seen some of that already as well. We had Faraday's law, which said that there is an electromotive force that's induced, and that is equal to negative the change in the magnetic flux over time. A time derivative of the magnetic flux. Change the magnetic flux and do something with the field, or with the area that's enclosed, or the orientation between some sort of surface and the magnetic field. Changing the magnetic flux, that can create current, for example, along a wire in a circuit. We can be a little bit more sophisticated, and there's going to be a little bit of math kind of swept under the rug here. Well, let's just imagine I have some sort of wire, and with it we can attach to it a surface. And the surface, I might just make it simple, and I might just make it the surface that is enclosed within this loop, this kind of 2D loop I've drawn. Right? It couldn't be really any surface, right? Imagine like a balloon. You blow up a balloon, and there's kind of that hole at the bottom, and then the balloon kind of wraps around. But nonetheless, there's a particular ring, that surface, which is the wire is playing the role here too. Let's draw it. Right, I can assume a surface maybe that looks something like, something like this. That is like that surface then is, in a sense, kind of defined. Its edge is defined by that ring. And then there's an inside of the surface and an outside of the surface. Well, let's stick with a wire. Let's stick with the wire. Again, if there is no battery attached, no capacitor, no nothing, and we looked at the magnetic flux that's going through this particular surface, the way that the magnetic flux changes then either could induce a current clockwise or counterclockwise, perhaps along that wire. Currents don't just move for no reason. Again, it can't just be the magnetic field, because you need moving charges to feel force from the magnetic field. So there must be an electric field that is being created along this path, along the wire. So there's something going on about an electric field that is parallel or anti-parallel to this wire, because then that is an electric field that will push current clockwise or counterclockwise in some direction. So, turns out, after a little bit of math, you can write this as the following. I can write Faraday's law as the integral of the electric field dot dl. So this is, to use the wire, right? This would be the electric field kind of along the wire is related to the change in the time derivative, or the minus the time derivative of the magnetic flux, which is then just B dot dA. And that is the surface that I've drawn. So that is a more fancy way of writing Faraday's law. A change in the magnetic flux, which is the right-hand side, can create a current, and currents being driven by electric fields along, in this case, the example of the wire. We then also have Ampere's law, which we didn't really go into detail, but then Ampere's law was able to find, essentially it was kind of a Gauss's law sort of thing with current, where he was able to write that the magnetic field across some sort of loop was equal to mu naught times the current enclosed. So this is actually an easier way when I write, if I draw a wire that has some sort of current. If I draw a surface that is defined by some sort of loop, some sort of closed loop, like so, it goes behind the wire there, then I can say something about the magnetic field along that blue loop. And that's how I could actually derive, like for example, when we show that the magnetic field, around a current carrying wire is mu naught times I divided by 2 pi r. So again, and we will just take that as a given. So these 4 equations end up being incredibly important. Let's write them down all together. Let me just copy them rather than rewrite them. So we have Gauss's law. We have no magnetic monopoles. We have Faraday's law. And we have Ampere's law. There is an exceptional amount of symmetry that's in these expressions, where you are saying something about the amount of electric flux and magnetic flux and how that connects to, in this case, charge enclosed and no magnetic monopoles. And then you have the third equation saying something about how if you change the magnetic flux, what happens? But then if you notice, the bottom equation doesn't really have something about how it doesn't have a change in electric flux. You would imagine if there's really good symmetry between all these equations, there'd be something about saying about there'd be some sort of time derivative of electric flux as well. So then there could be some equation that says, what happens when you change the electric flux? Maxwell noticed this as well. And James Clerk Maxwell then made the kind of intuitive, insightful breakthrough that you can assure amazing symmetry between these equations if you add one more term. That if I have epsilon naught mu naught, then I add in here a time derivative of the electric flux. So this was Maxwell's kind of insightful addition, eventually confirmed with experiments. That if you do that, then there is kind of this nice symmetry that goes on with these 4 equations. The first 2 saying something about the magnitude of flux, the second 2 saying something about what happens when you change the electric and magnetic flux. Also, the third and fourth equation, rather, the second pair of equations, are both saying change the magnetic flux, create electric fields. And the fourth one is now saying change the electric flux, create magnetic fields. These equations all arose independently of one another. Some were studying currents, some were studying electric charges, some were studying magnets. But Maxwell made the connection that actually, if you combine all of these together, it explains all of electromagnetism. So these are now called Maxwell's equations. You note, he didn't come up with any of them. He added one term to another to kind of bring them all together. But that insight, that was still nonetheless a giant leap step forward. There was no Nobel Prize back then, but had there been a Nobel Prize, this surely would have been awarded one. Because he took what were seemingly disparate phenomena and put them all together and realized if I talk about all 4 of these equations together, I can explain everything about electricity and magnetism. Electric fields, magnetic fields, currents, bar magnets, moving charges responding to magnetism. Everything is wrapped up in these 4 equations, which then is why we call it electromagnetism. These 4 equations describe everything. Of course, it took a lot to get here. Historically, it took a lot to get here. But nonetheless, these 4 things describe essentially this entire course and more. So, hats off to Maxwell. It took a lot of effort for us to get to this point, and we acknowledge his accomplishments. This really was a unification of electricity and magnetism. Now, and again, that insight really it should be applauded, right? You might think, well, he didn't come up with any of these equations. Why should we applaud him? But again, there's so many things out there, right? That if you can come up with a way to describe seemingly disparate phenomena through one kind of similar or one same sort of argument, in this case, by just combining these equations together, that is nonetheless a conceptual, theoretical step forward. But it's not like he didn't then do something with these. He then, of course, did very important things, once he realized that you can combine all these equations together. Particularly, he did this. Maxwell realized that, essentially, again, if you look at these equations, they are different. They are, well, in the way they're written down, they're integral equations. There's a whole another way you can write all 4 of these equations in terms of only derivatives, which is the differential equation version of these, which involves that Nabla triangle that we worked around with when we were doing potential. But I'm not going to worry about that now, because this section really is just kind of conceptual. We're just kind of talking big ideas. Like solving a differential equation, you're trying to find a solution, right, to the equation. Here we have 4 equations, so when we're trying to find a solution, it must be a solution that satisfies all 4 of these equations simultaneously. What he was able to do is Maxwell found a particular solution that gave a wave-like nature to the electric and magnetic field. All right, so he found a solution that behaved like a wave. What do I mean by a wave? He particularly found that if you have an electric field, or actually let me take one where you could actually go and do this. Find a magnet, which I don't have one nearby. Find a magnet and just shake it up and down. So if I find a magnet and I shake it up and down, I would create a magnetic field that has a wave-like nature. This is B. And I'm just shaking a magnet up and down here. You can imagine this kind of point being kind of where the tip of my magnet is. I would create a magnetic field that kind of ripples up and down, and it looks like a wave. And it has some amplitude, and how far apart these things are separated would depend on how fast I'm shaking the thing up and down, or if I shake it up really fast up and down, right, they'll be kind of squished together, versus if I very languidly do it, they'll be spread far apart. Now, a changing magnetic field creates an electric field, just like how a changing electric field creates a magnetic field. So by changing the magnetic field, by shaking this thing up and down, it turns out you create an electric field that is perpendicular to this thing and kind of looks like this. Now, it also kind of goes up and down, but at a 90-degree angle to the magnetic field. So this is the electric field. And they together propagate forward. So by changing the magnetic field, that creates an electric field that also changes. And then as the electric field travels, or as the fields travel away from your magnet, the fact that they're changing reinforce one another. So the changing magnetic field creates that electric field, but then that changing electric field creates the magnetic field, and then they end up kind of just traveling together as this wave-like pair that propagates forward. So I wanted to write some sort of equation down. It might look like E would look like something like, right, some sort of E naught. Then there would be some sort of cosine factor kx minus omega t, and that would be moving, let's see, kind of, if I put some axes here, it looks like, if I call that y, x, and z. So the thing is traveling in the x direction, but then the electric field kind of goes in and out of the page, so it would have some sort of z component, and the magnetic field is some sort of b naught, and it also would be some sort of cosine x omega t, the x inside the cosine because it's traveling in the x direction, but then it seems like it goes up and down, that would be in the y direction. Now, don't worry too much about these expressions. The way we have our intersequence modeled, we do waves and this sort of wave propagation stuff all in third semester modern physics, but I do want to write it down so it's not completely foreign when you see it in the fall. The takeaway is that I can write down an expression that tells me, at a given location, at a given x, or in a given moment of time, a given t, there is an expression that tells me the strength of the electric field and the magnetic field if they are created by this wave-like, if they are part of this wave-like solution. K is what's called the wave number, and it connects to something you're probably more familiar with called the wavelength, as 2 pi divided by lambda, where that is the wavelength. And then omega as what's called the angular frequency, and it connects to something you're probably more familiar with called the frequency f as 2 pi times the frequency. These things obey a particular dispersion relation. There's a relationship that if I know k and omega, that actually tells me the velocity, such that the velocity ends up being simply, in this case, omega divided by k, which then is 2 pi times f divided by 2 pi divided by lambda. The 2 pi's cancel, the lambda pops up top, so this is lambda times f. So that the velocity of the wave connects to the wavelength and the frequency. And this actually ends up being an expression that's true for a lot of wave phenomena. That's worth a highlight. Particularly the connection that velocity is just wavelength times frequency is what we'll need today. And so to give a little animation of this, before I drop the bombshell, here's kind of the idea. The axes don't exactly match what I drew on the paper, but that's okay. But essentially you have this thing that looks like a propagating wave. Like imagine taking a slinky and shaking it up and down a few times. Those ripples would leave you and propagate forward. It would be a transverse wave, in that notice that the electric fields and the magnetic fields are moving perpendicular to the direction the wave is moving. They are moving in the z and y direction, if you look at the GIF, while the entire wave is moving in the x direction. That makes it a transverse wave, of course, compared to a longitudinal wave, like a sound wave, where it's compressions in the same direction that the thing is moving. And you can notice that if you were to put your eyeball, like right here where my arrow is, you would notice that the electric and magnetic fields would oscillate back and forth at that point as it moves past your eyeball or past your sensor or whatever it is. Now, here's the big thing that, why this was a breakthrough. You say, okay, cool. He found the solution. That's fun. Then he calculated exactly what this velocity was. Let's see. I'm going to keep everything together, so I'll move this to the next page. So he calculated the velocity using Maxwell's equations. And he found that the velocity was v equals 1 over the square root of epsilon naught times mu naught in a vacuum, which also is pretty close to what it is in air. This evaluates to 3 times 10 to the 8 meters per second, or what we call the speed of light, which they already had a number. They already had calculations of what the speed of light was, but they had no explanation for what light was. They knew its speed, they couldn't explain what it was. Now they can. This allowed us to then declare that, aha, we have figured out what light is. Light is nothing more than an electromagnetic wave, an oscillating electric and magnetic field that travel together at the speed of light in a vacuum. As in these two oscillating fields, when they reach our eyeball, right, might be perceived as, say, the color red or some other color, or X-rays or gamma rays, or anything that is an electromagnetic wave. In fact, this entire electromagnetic spectrum could now be explained. This thing here. This entire electromagnetic spectrum, what I'll just call the EM spectrum, all just E and B waves. All just oscillating electric and magnetic fields, and depending on their wavelength or the frequency, they manifest themselves as either radio, microwave, infrared, colors of the rainbow, ultraviolet, X-ray, gamma. These are all the same thing. The only thing that differs in this case is their wavelength or their frequency. Let me point out let me define some stuff just in case we're not all on the same page with what wavelength and frequency correspond to. So let's take a wave that is traveling this way at some speed. The wavelength is just the distance from peak to peak or trough to trough. So that's the wavelength. Then the frequency is if I had a sensor here, and there's some sort of device or person that is paying attention and is just measuring how many waves pass by the sensor every second. That's the frequency. So the frequency is number of, you can think of number of crests passing a sensor each second. The units, wavelength is the distance, the SI unit would be meters. The SI unit of frequency is number per second, so just 1 over second, which we call a hertz. So, and what's nice is that for light, the relationship between them is very simple. For light, the wavelength times the frequency equals speed of light in vacuum. This general relationship of the wavelength times the frequency equals the speed of light, or rather, the more general relationship where wavelength times frequency equals velocity, again, that's a more general relationship where the velocity depends on the medium that the thing is moving through. So so the velocity of a wave, right, if it's a water wave or a slinky wave or a light wave, depends on the medium that it's passing through. So, and that's why I say in vacuum, because light does not travel always at the speed of light, 3 times 10 to the 8 meters per second. It moves a little bit slower in water, a little bit slower in plastic, for example. Just how sound travels at different speeds through different mediums. But thankfully for air is essentially, yeah, actually it is. I don't know if it's coincidental or if it, if there's something profound going on that, air in a vacuum share very similar properties. I'm sure that this has been explained somewhere. But let's do an example of, for example, red light. If I look at this diagram, red light seems to have a wavelength of, let's just use 700 nanometers. What is the frequency of red light? So e.g., red light has a wavelength of 700 nanometers, or 700 times 10 to the minus 9 meters, or 7 times 10 to the negative 7 meters. And then also I know that the frequency is the speed of light divided by the wavelength. So that is 3 times 10 to the 8 meters per second divided by 7 times 10 to the minus 7 meters. Meters cancel. My unit left is 1 over seconds or hertz. I'm dividing by a negative exponent so that they're going to add. So I know this is going to be 3 over 7 times, and then 7 plus 8 is 15 hertz. And so when I actually plug it in, it's something like 4.3 times 10 to the 14 hertz at the end of the day. Which again, what is frequency again? That means if you take a magnet, right, this is a ruler, but let's pretend it's a magnet. If I take this magnet and I shake it up and down once a second, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4, right? I'm creating a wave that has a frequency of 1 hertz. If I shake it, twice every second, that creates a frequency of 2 hertz. If I had the strength or the elasticity to shake this magnet up and down 4.3 times 10 to the 14 times every second, I would actually see red light come out of that magnet. I would be creating electromagnetic radiation. I cannot shake it that fast, so I'm not going to try. But that would be the case. So next time you go to a rave, right, take some magnets with you, and when you shake them up and down, you are creating radiation, right, as you dance around. And you can tell people that, and you probably won't ever get invited back to the rave again. But nonetheless, you are creating radiation when you do that. An antenna is essentially just, think of a long old school antenna. It is just shooting charges up and down at some frequency. That then is a changing electric field, which then creates a radio wave that gets shot out and travels then through space. That is the basic idea of an antenna. So this has profound impacts on everything that we do. That light is just an electromagnetic wave. All right. We are now going to then take all of this and simplify it and take the more Newtonian or Al-Halthian approach of old school kind of models of light and just treat light as a beam or a ray. So we're not going to worry so much about the exact nature of what the electric and magnetic fields are doing, but we're just going to model it as just a straight beam or a ray. And a lot of historical work went into showing that light travels in a straight line unless it interacts with an interface or if it transpires into a different medium, which is what we are going to talk about now. But just the idea that light travels in a straight line has a lot of interesting historical writing about it. Islamic polymath Al-Halthian, Newton thought about this. A lot of people thought about just the not the wave nature of light, but the ray nature of light. I believe Newton had some model where he thought light was particles, which at the point, after Maxwell, they figured was wrong. But then once quantum mechanics came about, and we saw that actually if you stare at this ray close enough, or if you stare at these waves close enough, it turns out to be a bunch of little things that we call photons that seem to interact a lot like particles. There was actually some truth to that. But let's now go into just basic ray optics. Something I think you will find is a nice respite in these last 2 to 3 videos. Because essentially now, Now we're going to talk about the electric and magnetic field again. We're going to just assume we're just going to model the ray nature of light as it travels from point A to point B, which might involve it bouncing off a mirror or going from, say, air into water. Since light travels at a constant speed, in a given medium. Again, it does not travel at the same speed in plastic compared to air. But in a particular medium, its speed is some sort of constant. In a vacuum, it's just the speed of light, 3 times 10 to the 8 meters per second. The kinematics, quote unquote, I guess, of rays is hella simple. Let's do an astronomy example. Here's the sun, here's the earth, and on average there is some distance between them, which we call 1 astronomical unit, but this distance is about 1.5 times 10 to the 11 meters, or about 93 million miles. How long does it take a beam of light to get from the sun to the earth? Not instant, even though light travels pretty fast. Once again, I'm at the bottom of the page. Well, if light is traveling at a constant velocity, this is pretty simple. Because then that means that the distance traveled, which is equal to the velocity times time, then just becomes the distance traveled is equal to the speed of light times time. Or that the time it takes is the distance divided by the speed of light. Since we're in space, we treat that as a vacuum. 1.5 times 10 to the 11 meters divided by 3 times 10 to the 8 meters per second. And it turns out to be, once you convert to minutes, about 8.33 minutes. If the sun could be shut off like a light bulb, then it would take 8.33 minutes for us to realize that that's happening. Why? Because essentially, if I were to turn the sun off like a light bulb, there's all that light that has already left the surface that is just on its way. It's just still traveling to us. And after 8.33 minutes, all that light would eventually have made it entirely to us, and we would see the sun go dark. So, really this manifests itself when you're talking about, astronomical distances. We will calculate in class how many times light makes a round trip from San Francisco to LA every second. Much faster than taking your car, for sure. All right, let's see. Other examples I want to do of that, those are pretty trivial examples. I think we need to really go into a lot of detail. So, now let's talk about reflection. So suppose I have a mirror, which is a thin piece of glass with some sort of silver or aluminum back, where that kind of shiny back end is actually what reflects the light. It's not the glass, not the glass of a mirror that reflects your light. If you were to take your mirror apart, right, it's a thin piece of glass, and then there's some sort of shiny reflective part on the back. And I shine a beam of light onto the surface, so this might be a mirror. And this is going to be our incoming ray. We expect it to bounce off the mirror, but how? How could we quantify how it reflects off the mirror? This is best done through some sort of experiment. So let me actually just show some simple videos that show this. With all respect to my colleagues who have made these. So here essentially we have a flashlight, but there is a protective, there's a black piece of metal blocking the flashlight except for a small slit that's cut into it. Essentially this just allows us to have a nice well-defined beam of light that comes out of the thing. And so what we're going to do is we're going to bring and put a reflective mirror next to it and see, as this beam comes in and hits the mirror, what happens to the light when it gets reflected. So there's our mirror. And again, you can kind of see that it's a little thin film of silver, and then there's a piece of glass to protect it. Then we do that. Aha! Look at that. It reflects, as we would expect it to do. So it seems to come in and then reflects out. You can see that there might be some angles we could define, in terms of how the reflected beam is reflected. Because it seems like when we do this, this angle seems bigger compared to when it there it's really big, compared to when we hit it when it grazes the mirror, it doesn't seem to reflect quite as much. So again, it kind of comes in, it's not my finger, but comes in, hits the mirror, then reflects back out. And now we want to understand what angles, if I knew how it came in, could I say something about how it comes back out? So let's move forward. They draw some lines, essentially is what you're going to do in lab. And we could draw, and essentially they draw something like this, where they have the idea of the light beam came in, it hit the mirror, and then bounced back out. And it turns out that you can define this particular angle based on the normal from the mirror. And let's see if they just define it here. Okay, yeah, this is good. Defines our terms. Angle of incidence, angle of reflection. Then let's pause it there. So what you notice here is that the light beam comes in, it hits the mirror, and then bounces back off. We can define a unique angle relative to the normal. So again, another use of normal vectors. Though again, we don't really have to deal with vectors in this case. But if we have a mirror, I can draw a line 90 degrees to the mirror and call it the normal line. And then I can have this angle here, so the incoming ray relative to the normal. We're going to call that the incoming angle, or the angle of incidence. And then it bounces off the mirror, and so then there's this angle here called the angle of reflection. And then you can measure things with a protractor, and you will notice that they match, and they always match. So let me actually make this drawing a little bigger so we can do something very similar to the video. So we have our mirror, we have some incoming angle or some incoming ray, and we have, as a result, some outgoing ray. The thing that we will do, so we will call this incoming, and this might be reflected. We'll put some arrows to help show that. Here's the mirror. I'm going to define my normal as perpendicular to the mirror. So again, I'll erase this after, so I don't want this to be too messy, but notice that there's a 90-degree angle between the mirror and the normal. Then I can define this angle here, which I'll call theta sub I, and theta sub I is the incident angle, or incidence angle, or incoming angle, and then there is the reflected angle. And the relationship is that theta sub I equals theta sub R. Man, isn't that nice? The derivatives of flux or Lenz's law or anything like that. For reflection, the incoming angle, the incidence angle, matches the reflected angle. What a treat. So then we can do, these are, I'm not going to do a calculation with numbers with this, but you can do some interesting ones, like what about for a corner mirror? So here's a mirror that makes, these are two mirror plates that form a 90-degree angle with one another. And I have some incoming ray that comes in this direction. What happens? Well, we can just take this in stages. I can create, I guess my normals were blue up there, so I should have made this not blue. See, can I recolor? I can recolor. Look at that. So let's have a so then it comes in and hits the wall and there's the normal, so it's the thing 90 degrees to the mirror. And then maybe this angle here is alpha. Then I know that what's going to happen is it's going to reflect such that this angle here is alpha. And then it's going to hit the top mirror, and then can draw a normal vector. And it might come in and hit at some angle beta, and then it's going to reflect at some angle beta. Now the way I've drawn it, it kind of seems like it comes back out in the same direction that it came in at. That wasn't just coincidence. That is indeed the case. We should be able to prove that, however. So, if I look at, for example, now we just have to find some geometry. I have the straight line here, and then I have a straight line here, and I have a line here. And, two parallel lines with a line going through them. Let me recopy that. So I have the mirror, the left mirror. I have the normal vector, which I'll draw as blue. The mirror I did not draw very straight. Let me try that again. Here's the mirror. Then I have the ray that went through both of them. So again, this part right here corresponds to this right here. And then this corresponds to this. And this corresponds to this. So then, what do I know? Again, I want to use similar triangles, ideally. So if I know that this is alpha, I might be able to then, it might be nice if I could relate the betas to something, right? So this then is beta, so then this I know is beta. And then if this is beta, then I know then this angle is beta. So then this is beta. So then it seems like if I look at this combination right here, I've shown that alpha plus beta equals 90 degrees. So, as a result, if I draw the top mirror as a dotted line, since this is also beta, again, if that's beta, then this is beta, then this must also be alpha. But when I think of the beam that gets reflected back off, That's the beam that kind of bounces back off. Since angle incoming equals, right, we said that these two are beta, so then this must also be alpha. So then going back to the original drawing, seems like this angle is alpha, this angle is alpha, this angle is beta, and then this angle is beta, just by geometry. So it does indeed kind of, if it comes in at an angle, if we zoom in a little, if it comes in at some angle alpha, notice it ends up bouncing back at some angle alpha. So, pretty cool, very simple. Now let's talk about transmission of rays through different mediums, or refraction. Now this is just going to be the bending of light, really the bending of light's path. Through two different mediums. I.e. the path that light takes when it goes from air to water, or from water to air, or from space to our atmosphere, these sorts of things. The light path appears to bend. The path of the light appears to change, right? And so the light beam appears bent. And this is why, for example, that a pencil stuck in water appears like the pencil is bent. We're not really talking about images yet, but essentially the image of the pencil that's submerged underwater, that image gets bent, as it makes its way towards our eye, compared to the part that's above water and just travels in a straight line from the pencil to our eye, and as a result, it appears kind of bent through, across the interface. So again, the idea here is that what really is happening is that the speed of light is changing. Across the medium. And we can quantify it in the following way. Instead of writing lambda times f equals the speed of light, we'll write lambda times f equals speed of light divided by n, where n is called the index of refraction. Again, n equals 1 for a vacuum. It's approximately 1 for air, close enough for air. It's about 1.3 or so for water. Plastics can be very similar. And these things can get very large, like looking at a book, right? It seems like, let's see, quartz 1.46, sugar solution 1.49, diamond 2.42. So these things can be calculated. And actually, there's a very easy way of calculating these things, which we'll do right now. So what this means is that when the speed of light changes when it goes through a medium, going back a little bit to the physics of electric and magnetic fields, the frequency, that ultimately ends up changing the wavelength of the light that's moving through. And so as a result, the kind of propagation of these waves appears to take a bent path. Again, I'll save that for third semester. What ultimately you end up seeing is if, for example, you're going from air into water, and you have a beam of light that comes in, you see that the path ends up bending and becomes, in this case, a little bit more steep. And again, we want to be able to quantify this. And we again always use the normal angle. So we have a normal that is perpendicular to the interface. Again, it's going to perpendicular to this interface between air and water. And we can define this angle here is the incidence angle. And then I could define this angle here as perhaps the refracted angle. Those unfortunate reflected and refracted both start with the letter R. So what I'm going to do instead is I'm going to call it theta 1 and theta 2. To give you, right, the order gives you a sense of the directions. Right? I'm going from air to water in this case. If it was the opposite, if I drew the arrows in the opposite direction, right, I'd be going from water to air. Then I might call theta 1 the one on the bottom, theta 2 the one on the top. And now air and water have different indices of refraction, so I might define this as N1, which in this case ends up just being 1, and this I'll call N2, which in this case is about 1.33. And is there a relationship between all of this? Absolutely. It's what's called Snell's law. That N1 times the sine of theta 1 equals N2 times the sine of theta 2. Again, a very simple relationship that gives you how the light beam bends as it crosses an interface. And the way I've drawn it, notice that when you go from kind of small to big N, that the light bends towards the normal. Right, it got closer, the theta decreased. And then as you go from big to small, again, imagine drawing the arrows in the opposite direction, it bends away from the normal. And again, let's show an example or two. Well, actually, I have a picture that I can use. I had a picture for the other one too. Whoops, forgot to show this one. Let me show that one real quick. So this actually is for, no, this is for both, sorry. And these pictures are maybe a little too small, but let me show it with some highlighting. Again, let's take this one on the left, right? You have some sort of light beam that comes in, and notice that it bends, and then when it goes back out into air, it bends again. So ultimately it looks like it takes a path that looks like that. And if we want to draw on it and to make sure we understand kind of what's going on, and if I were to zoom in here, again, seems like here is the interface, and so the normal vector, or the normal line is here. And so I'm going to use black, maybe like yellow or something, really bright. So then we have a beam that comes in, and then it seems to bend closer to the normal. And my hand is a little shaky. So we have this theta 1, and we have this theta 2 as a result. Then once it gets to the bottom, the same thing happens again. We have the interface, and so we have the normal. And so the beam kind of comes in, and then it bends back out. So then we have here, this would be the new theta 1, and this would be the new theta 2 as a result. And you could figure those out by solving the problems separately. So then again, with this here, we have our flashlight, which then creates an incident beam that comes in. It hits an interface at an angle. And so as a result, it bends when it goes from air to plastic. And then goes, so it bends in that manner. And again, if we draw some normal vector, I keep saying vectors, some normal lines. seems like we have our incident angle, theta 1, and then we have our refracted angle, theta 2. And it bends closer to the normal because plastic has a higher index of refraction. But then notice when it comes out here, we have this kind of semicircle interface here, that when it comes out here, it does not bend at all. Now, why doesn't it bend at all? Oh, I did not draw it perfectly. That's okay. Well, it doesn't bend at all because notice if I were to draw, let's zoom in. Oops, what have I done? If I were to draw the interface, the interface is here, and so the normal vector is along the same direction that the beam is passing through. So the incident angle is 0, and so the refracted angle is also 0. So as a result, it just travels in a straight line through. You'll also explore that in lab. But here we can see kind of some examples here. So, all right, we have here. Let's see when it's essentially it's 0, so it comes in at 0, and then there's no refraction. But then if I move it like 5 degrees, then it bends a little bit, and it's not quite the same. It's in the way. Let's see if we can make this bigger. So here it looks like I've moved about 15 degrees. So the incident, or the incoming, theta 1 is 15 degrees. But then the refracted is only about 10, closer to the normal. Just span through. Here it's 40, so it's coming in at 40. This angle is 40. But then it only comes back out at about 25. I go some more. Then notice something interesting is happening here. So I'm down to like 70 degrees. So 70 degrees comes in, it refracts, and it only comes out at about 40 compared to 70. But then notice part of it is also reflecting as well. That you might think that there should be a conservation law enacted here, that all this light comes in and then some of it splits, and some of it gets reflected and some of it gets refracted. Now, just by conservation alone, the total energy here better match this energy plus this energy. The relative amounts, don't worry about it for right now. But notice that more gets reflected as your angle gets larger and larger. It's kind of fun. Versus here, very little is reflected at all. Okay. Let me do a numerical example, and we're essentially done. All right, so for example, if it comes in and I'm told that the incident angle is 28 degrees in air, and then there's some mystery substance that it comes in, and the refracted angle is only 18 degrees. What is the index of refraction of this mystery substance? Well, I know that air is 1, so then you have n1 sine of theta 1 equals n2 sine of theta 2. n2 then looks like it's just n1 sine of theta 1 all over sine of theta 2, which then ends up being about 1.52 when you plug in the numbers. Not too bad. Now, the last thing I'll point out, what if I'm going the other way? What if I say I'm going from water to air, and I have a beam that is, let's see, maybe it's coming in at some angle. The previous example showed that it should bend away from the normal, so it should bend something more like this. here's theta 1, and here's theta 2, with theta 2 greater than theta 1. You might wonder, is it the case that you can adjust the angles, that you imagine increasing theta 1. As you increase theta 1, theta 2 increases. And if theta 2 is always bigger than theta 1, eventually you might imagine that theta 2 will become 90 degrees. So at what point do you have some angle that comes in? Maybe I'll do it in a different color. You have some angle that comes in, and then what ends up happening is rather than going through, it kind of ends up just grazing the surface. And then what happens when you go even farther? Well, then when you go even farther, so I increase theta even more, turns out that you get reflection instead. This is what's called total internal reflection. Right? Not because it hit a mirror, but because, going from water to air, there is an angle where if you shine the light at that angle, the image won't go through the water, but instead will bounce back. This critical angle, right? So this critical angle here, I'll call it theta crit. So what is theta crit? Well, we can just use Snell's law. We're going from, this N1 is this interface, and then N2 is that, which we know is less than N1. That is a requirement. And I should calculate what this is for water. I don't remember off the top of my head. We'll have to calculate it together real quick. Get Mathematica booted up. Gosh, this thing is slow. Okay. We'll have that at the ready. So by Snell's law, it looks like you have N1 sine of theta crit equals N2, then the sine of the angle looks like it's 90 degrees. If I'm just looking at the blue lines, that's theta 2. Well, sine of 90 is just 1, so that's just N2. And it looks like theta crit is the inverse sine. Well, actually, let me not do that yet. Let me just solve that. It looks like sine of theta crit is N2 divided by N1. Now here we can do a sanity check. The sine of an angle can only give you back a number that's between 1 and -1. So if N2 divided by N1 was, say, 3, then we would already know that this is nonsense. But we made the assumption that N2 was less than N1. So this entire thing is, by definition, less than 1. So that passes our sanity check. So then theta crit is equal to the inverse sine of N2 divided by N1. And that is the critical angle for total internal reflection. I'll get that highlight too. And again, notice it requires that you're going from a more optically dense medium, higher index of refraction, to a lower index of refraction. And then real quick, what is that for water? So then it looks like arc sine of, then we do 1 divided by 1.33. That is some amount of radians. So then let us do the same thing. Is it that for previous answer? Times 180 divided by pi, about 48.8 degrees. And you maybe have seen this. I think I have a picture of it. Yeah, something like this. Well, I guess I gotta get Mathematica out of the way. Here's an example of total internal reflection of, you're looking up kind of underwater, kind of looking up at the surface of the water where it goes to air, but you're at an angle that the image of the swimmer is going up, it's reflecting off the interface and then coming kind of towards you out of the screen, out of the page to your eyeball. rather than going exactly through. And you kind of can notice that the entire interface is showing total internal reflection. You're not seeing what's outside the pool. You're just seeing the ground, or the pool ground here, being totally reflected off the surface. All right, very good.